Or I could try to use Zoom for recording. Um, all right. The other things that you will find here are, if you go to files, you will find all the files that we have developed in class, right? So this is week 1, and these are the 2 files that we have developed, and you will see about 2 files for every week. Also, the files that are supporting assignments. Assignment 4 is not out yet. I'll explain why. Then we can go to the assignments, right? So there will be 5 assignments. The due dates are here. The due dates are optional. They're not firm, right? So submit at your own convenience. These are generally suggested so that you would end in the first, just at the beginning of the reading week. Right, but what I will really do is sometime during the reading week, I'm going to download all the files and start marking them, right? So don't overshoot this date, right? This is Monday, the Monday of the reading week. All right, very soon, towards the end of the reading week, I'll have to submit the marks. And I can't give you any more extension beyond that. Yes. So these will be the grades, yeah, and they depend. Each assignment is going to be a bunch of problems. Now, if you go to each of the assignments, right, there's no text here. You have to go to this file, and as you download this file, I'm gonna take it. Let's say if I'm gonna put it in Visual Studio. So let's just, oh, all right, let me just download it from where it actually is on the hard drive. So let's take assignment 1. Yeah. So you see that the file is formatted. These are comments as far as Python is concerned, but they essentially explain what you have to do, right? For every exercise, you have a template, and the body of the procedure that you have to write has this keyword called pass, which is an instruction in Python that doesn't do anything, right? It is provided precisely for this reason, to be able to specify templates for homework, right? Python being a teaching language at its origin. Right, so you have to replace this pass. You will have to actually remove it, delete it, and replace it with your solution, right? The problem has to, the definition of the procedure has to be the same. You cannot change this, all right? Also, read the requirement carefully, because you are expected to do exactly what the problem requires. One very common misunderstanding is that you print inside a procedure. If you look at all our files, we never print inside procedures. The keyword print does not appear inside procedures. I'm expecting the same. Print should not be inside procedures, right? The print, the testing, is done outside. The procedure returns a result, and I'm expecting that you will return a result, and right, there is a test for you, right? So if you run this in the interactive environment, right, you would see this. Yes, so this will serve you as a test. So you fill in something. Once your solution is ready, you should be able to run this in the interactive environment and see an output like this. So these are assumptions, sorry. Yeah, and you should see a result like this. The only thing that is printed, it should be the result. Actually, this is a bit I'm now realizing. I'm now realizing that this particular exercise actually asks you to print inside, which is exactly what I said it shouldn't do. But okay, you'll get the gist. Outside of so this will require you to print inside the procedure. Sorry. Man, this have been done quite a while ago. All right, so this will require you to print inside a procedure. The rest of them will not. So let's just give to assignment, make an exception for assignment 1. So starting from assignment 2, nevertheless, right? You will go differently, right? So for instance, you write the sum of positives, right? And we are evaluating this, and the result should be this, yeah? And so on, right? The sum of positives, we evaluate it, and the evaluation should be this, and so on and so forth, right? So everywhere, instead of saying what the output is, we say what the expression evaluates to, because inside these procedures we want a result to be returned. We actually don't want to print. Okay, hope that clarifies. I will go and change the text. Make it clear for assignment 1 that we do want to print inside, but for the rest of the assignment that we don't. Cool. So this is the pattern, right? You download the file, you start working with it, right? At some point, you're going to end up with a file full of solutions. And then I would like you to rename the file. I mean, it can remain assignment 2, but dash your metric number, right? So something that makes it clear that this file is yours. At the upload time, the system will record whose file this is as well, but it's a lot easier for me when I transfer the marks from the file into the system, the IMMS system, to have the marks in the owner in the name of the file as a metric number. It doesn't have to be in the name. Cool. Questions here? Yeah. So this being said, let's move on to today's lesson. So where did we stop last time? We did this equation solving. A little procedure, right? So let's go to creating a new folder, mkdir week 2 Thursday. So we go inside here. This is where our files are going to be. Okay. In our workspace, we see that this folder has been created. Inside here, we're going to have a new file. We're going to call it problem solving. .py. Today we're going to look at a few problem solving cases, right? And I'm going to try to explain what that is. So problem solving is not specific to computing. I'm just going to move this because it kind of blocks my view. So you often are faced with a problem that you need to solve, and that solution requires you ordering certain operations, right? For instance, you need to sort a deck of cards, yeah? Or you need to solve a puzzle, right? All these are problem-solving situations. And it's very important, once you have figured out a solution, to be able to write code potentially that solves it for you. But the important part is, how do you go about solving the problem, right? How do you tackle the problem at all? And we're going to try to go through a few examples, and hopefully that will help you appreciate the nature of algorithmics that go into computer science. The first problem that we want to solve is the problem of counting change. All right. So let's say we have n. Maybe no. Let's not start with counting change. Let's not. Shall we start with counting change? Okay, let's start with counting change. We're going to come back to counting change anyway, so we're going to do it in two instances. Let's say we have an amount of money, right? Expressed in cents, not in dollars, rather in cents. And somebody wants us to help them change the money that they have into coins, right? So as in many countries, the coins are only amounts less than $1, right? Here we still have a $1 coin. In a lot of countries we don't. So we're going to just assume that we have the denominations of, what are they now? 5 in Singapore. I actually haven't seen coins in Singapore for a very long time. 5, is there a 10? Yes. There still is a 10, right? 20, 50, that's it, right? Yeah. In the States, I think there's 5, 10, 25, and 50. Yeah? And in how many ways can we return change? So let's say if the amount is $1, one way of returning change is 2 50s, 2 50-cent coins, right? Another way of returning change is 150, 2 20s, and 110. Yeah? Now, the 150, 2 20s, and 110 is the same as 2 20s, 150, and 110. So the order in which we give the coins doesn't matter, right? The coins are seen as a set. So we want to count in how many ways, right? This is a problem that is not really related to computer science, right? But it turns out that it's very difficult to solve without a computer. All right, so it shows something very interesting about coding. How would you solve it? And while you think about that, let me set up my little contraption here, because I might want to draw a little bit. So let's say if I have an amount of 15 cents, assuming that 15 cents is, let's say I write a check of 15 cents and I come to you and say, give me change, or allow me to cash this check, right? So you can have a 10 and a 5, or 3 5s. Yeah, that's about it as a way to return change. Not everything has a way of returning change, right? So if I have 13 cents, I have no way of returning change for that. So how would you, so the amount of 15 is relatively simple, right? Because it has only 2 solutions. How do you go about to count? Right, and how would I count number of combinations? Okay. So it's a problem of decision making, right? The one thing I don't know in this app is how to delete. Okay. I can delete with delete. So let's say I have 15. Maybe a yellow will make it better, more visible. So I have an amount of 15, right? What decision can I make here? I can use a coin of 10 cents. Let's assume, I mean, I can assume that the coins, available coins are 50, 20, 10, and 5, right? But because the amount is small, let's assume we only have 10 and 5, right? So I can decide to use a 10, use 10, or do not use 10 at all. So these are binary choices, yeah? So if I have used the 10, I have already returned 10 cents. It means that I'm left with an amount of 5. If I decide to not use 10 at all, I am still left with 15 cents. But from this point on, I can not use 10 cents ever again, right? So if I have this amount of 5, I could use a 10, and I could say you try to use 10, and I could, right, because I'm allowed to use 10, I could try to use 10 again. Use 10, right? But then I get to minus 5, and minus 5 is not really an amount that I can. What I would want to do is reach the point of 0, right? That would be an amount that. So this represents my debt to the person, right? And a debt of minus 5 would not contribute to a solution. So use 10, or again, not use 10. Right. So in that case, I'm left with 5. Then the only choice is to use 5, and then I am left with 0, and this is a solution, right? And then you can see that I have one way of counting change, right? I have a 10 and a 5, or not use 5 at all. So then I'm left with 5 and no choices, right? So here I have no choices. If I go to this 15, I'm just going to put it here 15, right? I can continue, but now I cannot use 10 at all. So I can use 5 or not use 5, no 5, right? So no 5, I'm left with 15. Here I'm going to have no choices, right? So this is not a solution. I use 5, I'm left with 10. Then again, I have two potential choices, use 5 or not use 5 at all. Right? Then no 5 is going to leave me with 0 solution. If I have 5, I'm left with 5 here. And again, I have two choices. One doesn't leave me with a solution. The other gets me to 0. And in this way, right, looking at this tree of decisions, I see that I have two places where I ended up with a 0. And the path from the root to that 0 gives me the combination of coins, right? So I use a 10 and a 5. That's one way. The other is if I go here, I use a 5, and I use another 5, and I use another 5. Yeah, so I have 3 5s. And because this was a very small amount, I can draw the entire tree, but the tree can actually be very large. So if my amount is $1, so it's 100 cents, right? And I have 4 coins rather than 4 denominations rather than 2, right? I'm going to have a lot more choices. So I'm going to start with use 50 or no 50. So it's not so predictable what's going to happen, yeah? But nevertheless, this is a strategy. So now I don't care of the fact that I can, as a human, cannot predict, right? I can put a computer to do all these calculations, and I'm going to get a number out of it, yeah? The important thing is that in this decision, it's very clear that I have not counted anything twice. I have not missed any combination, right? Why? One, we were very orderly. We considered all the denominations in decreasing sequence, but actually that doesn't even matter, right? Even if we didn't look at them in decreasing sequence, we would have reached a solution, right? And we are always having binary choices. So it's either I can do that, or I do something that is completely disjoint. It's the complete complement. There's nothing in between that is left to be, there's no little choice that I missed here. I can either use a 50 or never use 50 at all. Yeah, so that's very clear. That's the choice that I'm making, right? So in making this kind of choices, I am very sure to explore the entire solution space. Yeah. So then what am I going to have here? Well, here I'm going to have the same problem, but for a different amount and a different number of coins. Again, the same problem, but for a different amount and a different number of coins, right? So we're going to, of course, use recursion. When do we have a solution? When the amount is 0. I don't care how many coins I am still allowed to use. If I reach 0, it's a way of returning. When I know that I can stop and I have no chance of finding a solution, right? Any further exploration is not needed because I am outside of the boundaries of finding a solution, right? When I get a negative amount, right, obviously the amount is only going to go further negative, right? So if I have overshot the value of 0, I'm done. I will never get back to 0. Or I have run out of coins that I really can use, right? Because every once in a while, I will say, oh, not use 50 at all, right? So my choices here are going to be restricted from this point on. 20, 10, 5, right? Here I can still use all of them. 50, 20, 10, 5. Yeah? So, at some point, if I keep going and I don't find a solution, this list will become empty. At that point, I have I have a positive amount, but I have no denominations left to use, and then that's not going to lead to a solution either, right? I can't go forward. Is this clear? A lot of solutions in computer science is about making choices, and it's essentially problem solving is about making choices and making sure that you don't make the same choice twice and you don't miss a choice that you might have made. So let's try to put this in code. I just want to hide this. Okay, so count change. So we're going to have an amount, and we're going to have a list of denominations. Okay, so whenever we write code, we have to make sure that we finish, that the computation terminates. So we look at the base cases, right? Even though the base cases are not what we encounter first, right? We look at what's at the bottom of the tree, right? At the bottom of the tree is if the amount is 0, return 1. So if the amount is 0, I have found a way of returning change. If the initial amount is 0, I have a way of returning change, which is giving you nothing, which is what counts as one way. Yeah, I'm giving you that something called nothing. So I'm giving you something, and therefore it's one way. Yeah. Now, if amount is less than 0, or if denominations is empty, and the way to check whether a collection is empty is to check whether its size is 0. There's no solution, so we're going to return 0. Yeah. Otherwise, we return count change of amount. So, amount minus denomination 0, right? So we used the first denomination, and we still are allowed to use all the denominations. Okay, plus count change we don't use that denomination. So what is left to use is everything except the first element. Yeah. So notice that the solution is actually extremely simple. You're going to ask me, why do I have a backslash here? So Python sometimes cannot detect that the current expression is not completed, right? And it is continued on the next line. And this backslash, which has to be the last character on the line, tells Python, oh, this line is not complete. Look at the next line, right? It has to be the last one, right? Notice that as I press on the right arrow, I'm going to the next line, right? If you have spaces here like this, then it's incorrect. So I'm right after the backslash, and I press, and I'm not on the next line. This is wrong. And you see that the my editor is getting upset and highlighting that backslash because it's not the last character on the line. It has to be like this. Yes?
What is len?
Len is length, stands for length. Now, because most typically we want, in terms of size, we want the length of a list, right? The list is a sequence, and it has length. You can speak of the length of a list without making a mistake, yeah? But if you apply it to a set, sets don't quite have length, they have size. Nevertheless, the notation is consecrated, right? So anything that resembles a connection or a collection and has multiple elements inside, right? The number of those elements that are inside, which is the size, it's accessible via this len, right? So if denomination has 4 denominations, this will be 4, right? As I go from here to here, notice that this is only, we're removing the first element from the denominations, yeah? So the denominations become smaller. Since it becomes smaller, it is foreseeable that at some point it becomes empty, at which point this becomes true, and we're going to return 0. Yeah. A way to avoid backslash, which is ugly, but it's actually the standard way, is to add brackets. So if you open a bracket here, and not all the brackets are closed, Python is smart enough to figure out that the current line is incomplete. So this is another way to write the same thing, and it's probably, some people will prefer it. However, if you write code for a living, and you write Python, there is such a thing, interestingly enough. The recommendation is to write it in this way. This is how professionals would do it. I don't write Python for a living. Disclaimer, never did. And don't quite consider it to be the suitable language for production. Yes?
No, I don't know. Why did you put that return statement outside the other return statement without any like else command?
Oh, so if I could say elif. So this will be perfectly equivalent. Elif and else. This will be perfectly equivalent. The problem is not a problem. It's just a shortcut, right? If I hit this return, I leave the function, I never reach here, right? So whenever I have return, I don't have to have an else. It has the same effect, right?
So it's just to make it shorter.
It's just to make it shorter, yeah. It's like a shortcut. Yeah, and generally shorter programs are better. That's the general agreement among professionals. So we're trying to write shorter code. So let's check that what we are saying is correct. So we're going to check for a few small values for which we know what the result is, right? So we're going to say print ways of returning, the number of ways of returning change for, let's say, so we tried 15 with denominations. And this time I'm going to put all of them, right? So 50, 20, 10, 5 is. All right, so because it's a very long string, I'm going to break it. All right, and I don't need to use a backslash because I have brackets. And I'm going to say here, count change 15 and 50, 20, 10, and 5. Okay, we can go to our command line. Notice that the file is there. Python 3 problem solving. All right, so we have two ways, which is something we already know. All right, let's try 20. So for 20, we have 4, right? So we have two 10s. We have a 10 and two 5s. We have 20. So just the 20, just 120. So you give me a 20, I give you back 120. Right? Two 10s, one 10 and two 5s, and four 5s. And let's do 100. Let's do $1. Oops. And this will gonna be 100 cents. And this is what I was telling you, right? The answer is 49. Is this the correct answer? Hard to know, unless we actually start enumerating all the different combinations, right? But that will be very time consuming, and I can make the amount even bigger, right? I can go to $10. It will be even larger number, right? So it's very hard to predict what the number is going to be, right? Nevertheless, we reasoned about this algorithm, right? We understand it's very simple. We know it's correct, right? We have checked it for small numbers and it works fine. So now when we apply it to 100, right, we get a result which we couldn't have predicted, computed in our own mind, and then we trust it. Yeah. So the computer essentially helped. It's not just a crutch. It gave us a piece of information which we didn't know before. We couldn't have had easily before. Questions? Next problem, Towers of Hanoi. Have you heard of this problem? So every time I search it, and I get a different, game, right? So here are the rules, right? There are 3 poles and the number of disks, right? The number of disks is in general n. You see 3 of them now, right? But the number can change, and I can actually vary it. The rule is that you can move a disk on an empty pole, or you can move a smaller disk on top of a larger disk. This is the rule. You can't move a large disk on top of a small disk. And you have to move all the disks from this leftmost pole to the rightmost pole, right? So you can make moves like this, right? And seems relatively complicated, and it's going to get more complicated as I add more disks, right? So if I go to 4, right, I have to go through this complicated set of moves. Yeah, come on. All right. How do we solve this? And it probably has an automatic solution. Let's see. Okay, right? So you can take this and have it as a new screensaver if you want. How do we solve this? So let me first tell you that the problem is intentionally misleading. All right, and that's often the case. So in practice, often you will find problems that are misleading, probably not intentionally, right? But this one is intentionally misleading, right? We're saying move the n disks from the leftmost pole to the rightmost pole, right? But the problem has a lot of symmetry. Why necessarily the first one from the first one to the third one, from the leftmost to the rightmost? I could formulate the problem as moving it from pole A to pole B, where pole A and pole B should be specified later, right? I may want to move it from leftmost pole to the middle one, leftmost pole to the rightmost one, middle to rightmost. Doesn't really matter, right? There's symmetry. I should be able to translate easily the solution, right? So why formulate it in such specific terms, right? So what we do here is we do a step called generalization. We are generalizing the problem. Instead of fixing some of the input, pole leftmost and rightmost, pole 1 and pole 3, we're saying, oh no, let's move it from A to B, yeah? So you're going to be surprised, but this is actually simplifies the solution, makes it easier to solve it, right? Generalization in mathematics is a simplification tool. It's not a tool that makes things complicated, right? Examples of simplifications or generalizations are infinity, all right? Infinity is an abstraction, of course, makes things simpler, not more difficult, actually. The density of real numbers, right? The fact that in between any two numbers there's another one, right? Turns out that matter is not. It doesn't model real nature, right? Matter is discrete. There's, at some point you get down to one atom, and that you can't go into the middle of the atom. You can't take half the atom, right? But we have invented that, right? And that led to mathematical analysis and the notion of derivative and integral and so on, which are very useful in computing stuff, right? They're actually approximations of the real world, and they simplify stuff. They don't make it more complicated. Complicated as it is, it would have been even more complicated without them. So what do we do here, right? There's another interesting property. We have 5 disks now, yeah? Can I assume that the big disk, the largest disk, doesn't exist? Yes, if I assume that that doesn't exist, it just sits there, any move on top of it will be legal, right? Because it's the largest. So I could have 5 disks, but envisage to solve the problem for only 4. Yeah? And any move that I conceive of will be legal because the largest disk, right, is as if it wasn't there, right? So, right, how do we solve the problem, right? Well, I want to move from pole A to pole B using pole C as an auxiliary, right? Now, what if I try to solve the problem for 4 disks and I try to move from A to C? Same problem, different inputs, right? So if I manage to do that, I take 4 disks and put them in the middle. Then I will remember, oh, the largest disk exists. Let's take the largest disk from here and put it on the 3rd one, right? Why? Because all the other 4 are here in the middle. So the largest disk can move from the left to the right. And then I'm going to forget that the largest disk exists again. And I'm going to say, oh, now I want to move 4 disks from the middle to the 3rd one. Same problem, different inputs, yeah? So I can actually express the big problem of 5 disks, right, as solving the problem of 4 disks from the same source but a different destination, plus moving the large disk, plus again moving 4 disks from that different destination to the original destination. Yeah? And then the problem of 4 can be expressed in terms of problems of 3, and the problems of 3 in terms of problem of 2, and the problem of 2 in terms of problem of 1, and the problem of 1 in terms of problem of 0. And the problem of 0, we know how to solve. What do we do when we want to move 0 disks? What do? I do this. Yeah? That's all I have to do. I do nothing. Yeah? I do that something called nothing. All right, cool. So, so the easiest way to figure that works is, let's look at moving 2 disks, right? Oh, I can't move less than 2, right? So let's move 3, right? So let's see the strategy that it works for 3, right? So I'm going to move 2 disks. I'm going to move 2 disks from the leftmost pole to the middle pole. Yeah. Now, in moving 2 disks, so I need to move 2 disks from here to here. But in moving 2 disks, let me move 1 disk from here to here. Yeah. So I'm going to move 1 disk from here to here. So then I can move the largest disk because now I am in the. So I forgot that the number 3 exists. I forgot the number 2 exists. Now I'm remembering the number 2 exists, right? Put it here, and then I'm moving again 1 disk. So what did I do? I have moved 2 disks to the intermediate destination. Now I can move the largest disk. And now I can apply the solution for 2 disks from the middle one to the rightmost one. Exactly the same. Yeah? So when I want to move them from the first to the third, there will be a middle of the solution when all n minus 1 disks are here. Has to be. Yeah? So, We're going to write a first approximation to this solution that uses printing inside the procedure. All right? Why? Because we don't know yet. Well, we haven't. We're going to learn that soon. How to operate with collections. But we're going to learn that later today. Well, maybe not later today. So we're going to come back to this and solve it in the right way. Yeah? So again, I'm going to go away from my very lofty principle of don't use prints inside. We're going to use prints inside temporarily. Def Hanoi. So we're moving n disks from pole A to pole B with C as a intermediate destination. All right? So if n equals 0, right, do nothing. So I could do this and it's okay, and a lot of people actually would like it this way, but I'm not gonna, because it's a bit ugly, right? So if n is 0, remember, we don't have to do anything. If n is not 0, we have to do some stuff. So we're going to do Hanoi. We're going to pretend that the largest disk doesn't exist. So we're going to move n-1 disks from A to C using B as an intermediate. Yeah. So when this is finished, right, n-1 disks are on the middle one. Then I can move the largest one from the leftmost to the rightmost. And we don't know how to do graphics yet, so we're just going to say print move a disk from, we're going to find better ways to do it, from A to B. Hanoi n-1. And now, where are all the these n-1 disks? Where are they? Where are they? They are on C, yeah? So I have to move them from C. And where do I want to move them originally? I want to move them to B. Yeah? So I have to move them to B using A as an auxiliary. And this is Hanoi. Again, extremely simple. Something that looked very complicated, but it's actually quite simple. All right? So I'm going to write the solution for 15. Print and then I'm just going to note that I'm not invoking Hanoi inside the print, which is what I would do normally. 15, and we're saying from pole 1 to pole 3 using pole 2 as an intermediate. Yeah, and let's run this, see the solution, and verify that it is the correct solution. No, not 15, not 15. Four disks. I'm sorry. Right, 4 disks which will have 15 moves. 4 disks will have 15 moves. I will soon ask you how many moves will there be, right? So this is the solution, yeah? So let's verify that this solution is correct. We're going to go to the website and follow this solution. All right, restart. Let's do 4 disks, right? So we're having 1 to 2, 1 to 3, 2 to 3, 1 to 2, 3 to 1, 3 to 2, 1 to 2, and now we're in the middle. Notice that there are 15 moves, right? If you count them, there are 15. So we have gone through 7 of them, I think, up to here, right? And now I can move the disk from 1 to 3, right? So this big disk gets moved from 1 to 3. We're right in the middle. And then we have to take these 3 disks and move them to the third one as well. So the remaining 7 moves will do just that, right? So 2 to 3, 2 to 1, 3 to 1, 2 to 3, 1 to 2, 1, 1 to 3, and 2 to 3, right? You notice that they are smart. They know that the minimum moves is going to be 15. All right. How many moves do you think there are? So if n is the number of disks, how many moves will there be? Well, if we look at a code, which would be fantastic if I could access my, can I just access the brush thingy? Okay, if I make it visible, and then I go here, and do I, okay, wonderful, I get it. So, all right, so if n is 0, right, we would have 0, a cost of 0, right? There's nothing to move, right? So the question is how many moves, right? So let's denote by k the number of moves, and then k0 is 0, yes? And then kn is going to be equal to, so this is Hanoi n minus 1, so it's going to be kn minus 1 plus 1 move, and then plus another kn minus 1, so this is going to be 2 times, yes? So I have this kn, which is the number of moves for Hanoi n, yeah? So from these two, if you remember your discrete mathematics, no? I'm talking foreign languages. Yeah? So from this, you will find out that kn is 2 to the power of n minus 1. Yeah? So k4 is going to be 15, which is why, how they know that the number there is going to be 15. Okay? So notice that the solution is exponential. The magnitude of this is exponential, yeah? Exponential in general is, if we have to deal with computation time, exponential is bad. Yeah? It grows very fast. So if I have 100 disks, I'll probably spend something like centuries to solve the problem. You know this. There's this story about the chessboard, right? So apparently the guy who invented chess went to a king, and went to it's an Eastern story. I think it's an Arabic story, right? And taught him how to play chess, and the king was so delighted and thought that this is going to be he will have such fun spending time playing chess that he wanted to reward the guy. And he said, look, ask anything you want. Do you want your weight in gold? And the guy said, no, I want much less. I want 1 grain of wheat for the first square, right? 2 grains of wheat for the second square, 4 grains of wheat for the third square, 8 grains of wheat for the, what's next, fourth square, right? So he wanted essentially 2 to the power n minus 1 grains of wheat for square number n, yeah? And this adds up to 2 to the power of 64 minus 1, right? And this that time, assuming this was an antiquity, would have been the crops for many centuries, right? So if you took the crops of the entire planet at that time gathered in one year, this would have been several centuries worth of crops, right? So it's the trickiness of the exponential. Anyway, so exponential, bad, nice problem to solve. It's a very typical problem solving problem, and that's why we talk about it. All right, let's do another one that is a bit more mathematical, right? So permutations. Permutations are actually available in Python as a primitive, but we're not going to take advantage of that. And using permutations, we start talking about competing with lists, with collections. And actually, let's not do permutations first. Let's do subsets. Let's do subsets first. So what are the subsets? If I give you the list of 1, 2, 3, or the tuple of 1, 2, 3, right? What would be the subsets of 1, 2, 3? Well, it's the empty tuple, tuple containing 1 only, tuple containing 2 only, tuple containing 3 only, tuple containing 1, 2, tuple containing 1, 3, tuple containing 2, 3, and tuple containing 1, 2, 3. Yeah, all these are subsets, and they're in a relatively nice order. We don't have to get them in this order, but these are the subsets. How do we compute a subset? Again, very interesting problem-solving problem. Well, let me look at a smaller set, right? So let me look at a set 2, 3. All right, let me write 2, 3, right? So again, I have the empty set. I have 2, I have 3, and I have 2, 3. What's the relationship between this and this? Not only it is a subset, but there's more.
You can separate them with commas.
That was oversight. One more important property. Okay, let me look at the set containing only 3. So the subsets of the set containing only 3 is the empty set and the set containing 3. Yeah. So what's the relationship between this and this? Which is the same relationship between this and this. Yes?
They're all 2 times the power of the elements.
Very good. So it doubles in size, right? There's one more important thing, right? So you see, from here 2 is missing, right? So for each guy in here, there are 2 guys in here. For each element in the smaller one, there are 2 elements in the bigger one, right? So this guy, I have here this and this, right? And the second one involves the 2 involves the missing element, right? So this is for 2, 3. and this is for 3 alone. And this is for 1, 2, 3. Yeah. So if I take, so between this guy and this guy, right, there's the addition of 2. So if I take this guy, I have an instance of this, and I have an instance where I have added 2. So empty plus 2. Then for this guy, I have the same thing, and I have an instance where I have added a 2. Yeah? The same between 2, 3 and 1, 2, 3. Between 2, 3 and 1, 2, 3, this has an extra 1. Yeah? So for this, I have a copy of this and another instance where a 1 is added. For this, I have a copy of this and another instance where a 1 is added. For this, I have a copy of this and another instance where a 1 is added. For this, I have a copy of this and another instance where a 1 is added. Yeah? So that's the relationship. So now I can write my program. So I'm going to say def subsets of a tuple. And if the tuple is empty, right, so if len t equals 0, we return what?
Oh, 1. So number of subsets is 1.
Number of subsets is 1, but what is, we're not interested in the number of subsets. We're interested in the actual subsets. So that the only element inside the subset is the empty tuple, but I have to return the tuple returning the empty tuple, right? Because that's what we mean by the collection of subsets. I return a collection where the only element is a subset of empty. Yeah? Otherwise, right, I'm going to say smaller equals subsets of t, and I will take only all the elements except for the first one. Yeah? And then I'm going to return, so every element in smaller is also an element of the current solution. Plus, so every element in smaller is also an element of current solution, right? If I have a subset S for S in smaller, what do I return here? Well, I return T0 and T0 cannot be, has to be a tuple. Yeah, so exactly as we said before, right? So if I have the subset of 1, 2, 3, all the subsets of 1, 2, or all the subsets of 2, 3 are also elements of subsets of 1, 2, 3. And then what do? For all these guys, I take the element that I forgot, T0, and I put them inside every element of the smaller ones. Okay? So, print of 1, 2, 3 are, and we're going to say sets of 1, 2, 3. So let's see what the result is. Oh. So strangely, whenever I use these brackets, it doesn't figure out that this is a tuple. So we want to explicitly say that this is a tuple. All right, the subsets of 1, 2, 3 are, right? And unfortunately, we don't get them in the nice order that we initially had, but you can check that all of them are in. And when we talk of subsets, the order is not that important, right? So we can accept a random order. Cool? So we're going to stop here for tonight. We're going to talk about combinations tomorrow. All right, and then we're going to revisit the counting change and Hanoi. And instead of printing out results, we're going to, or just counting solutions, we're going to collect all the solutions in a collection, right? So we can see the actual solution. Cool. Questions?
Could you go back to the code for subsets?
Yeah, I'm going to stop the Zoom. Are there any questions? I should actually announce that we can do questions. We should do questions somewhere. Wait, I think I'm the only participant. Anyway, so next week, remember, we're going to have remote learning. I have no choice.